The video, she needs it. Hey, Jacqueline. So, beginning of class today, what we did was, and anybody gone? No, everyone's here. What we did at the beginning of class today was give them some time to go ahead and start writing down notes on slope field. They wrote down the first 3 slides, basically, of the Jamboard that is now in your guys' Jamboard for those of you that were listening. It is now there, but it only got up there like about 5 or 10 minutes ago. Meanwhile, in that Jamboard from Chapter 4B, the integration has net changed. There are now attached the answers. And with those answers in there, go ahead, Jacqueline, when you're done, go ahead and grade it with your colored pen. You can ask me any other questions that you might have as to why the answers are what they are, but go ahead and attach a screenshot of it done and graded, okay? Everybody here in class, I'm going to come around and mark it as done for you. Mark it as done for you. As soon as I show you, let me go ahead and get you going on an example. Then I'll come around and grade that worksheet. So keep your worksheet out. Actually, why don't you just pass it up, and I'll pass it back to you before the end of class. Is that cool? Worksheets, pass them up. And if it's in like a notebook, you can pass that notebook up. Pass the notebook open.
Do you want the actual workbook as well? Like, if you put on this
Hold on. So you guys didn't, you did it like in a notebook and done?
Yeah. I just
put his answers on there, but yeah.
Okay. I was thinking that you guys wanted me to like collect it because it was that way. I'll just walk around and spot check it. That'll be easier. I thought I was just collecting lots of worksheets, but I'm not. I'll come around and check it in a little bit. All right, here we go. Let me get you guys going on 5.1. Just keep it on your desk. Cool? Keep it on your desk. Oh, all right. It's not you guys. I'm just getting a headache because I haven't had coffee, and I've been having to project a lot in class today. So it's not you. Just trying to keep myself alive to Algebra 1B today. Is that cool? Testing. 1, 2, 3. Let's go. Section 5.1, slope fields. Minimal effort with a microphone, maximum output. So, very beginning, definition, it says, a graph showing a family, aw shucks, a family. Question. Families are blessings, they also have issues. Shout out to the psych discussion yesterday. Coming back. Where have you seen the word family this semester in math? It's been there, but where? Huh? Oh, I thought you didn't answer, and I was ready.
Oh, no. It's just...
Oh. I'm listening. Anybody that has input? Bunch of graphs. Where was there a bunch of graphs? Now, in pre-cal, were there families of graphs, like the trig graphs, families of graphs, like the quadratics, families of graphs, like the linears? Like, those could be families, but that wasn't this year. Where did we see family this year? We didn't technically say family of derivatives, but you're close if we think Spider-Man. Family of? Why? Why is that your reaction? Just be like, oh, hey, it's something that's special to me that I can remember. It's a family of antiderivatives. What? Why were the antiderivatives called families? They all look so different. Like, I mean, sure, there are rules. It was all because when you take a general antiderivative, you don't know exactly what the answer is, and so you put a plus C. And all of a sudden, when you put a plus C, you have a whole family of solutions. So where we've seen family before is whenever we had to do a plus C. We've seen this before, family of antiderivatives. It isn't new. It was why we had to do the plus C, which for some of you guys in your forever quizzes is different than the U prime, because the U prime was for derivatives, and the plus C is for antiderivatives, however you want to go with that. But guys, what do you see that's different here? What's the definition of a slope field? It's not a family of antiderivatives, it's a what showing a family of antiderivatives?
graph.
It's a what showing a family of antiderivatives? It's a graph. Some people call it a direction field, some people can call it a vector field. It can be applied in different ways. But it's a graph showing a family of antiderivatives shown by line segments with slopes. So line segments, it's a graph of line segments showing this, but a graph of line segments. Huh? I don't get it. With slopes determined by, okay, here's the calculus. Lines, we've been doing that since forever. Graphs, okay, I mean theoretically a graph of a line, once again, doing that forever. It shows a family of antiderivatives, but that's just what it shows. Where's the calculus? Right here. Slopes are from the differential equation. Slopes are going to come from where slopes always come from. The derivative, which can be seen as a dy dx or it can be seen as a y prime. The purpose is to provide a visual perspective of the solutions to. So the solutions to, well, we're going to talk about that on the next page. What are the solutions to differential equations? PS, differential equations, the equations involving x's and y's and the derivatives of y's. So over here when you guys were writing down general versus particular, we're answering the question, who are these solutions that we're visualizing? And PS, the entire chapter of 5, which was 5.1, 5.2, 5.3, 3 sections. That's it. 3 sections, 5.1, 5.2, 5.3 is all that we need to do. The entire title of chapter 5 for your table of contents is differential equations. Differential equations. These are the big guys. So we're talking about them, we're introducing them, and we're going to be visualizing them in graphs before we start solving them. Even though you've technically already solved a couple before. For the differential equation down here, why is he a differential equation? Well, because he has x's and because he has y's, well, so do lines. But what else does he have? Exactly. Okay, that's a differential equation. We're in calculus now, right? He has x's, he has y's, he has constants and minuses and equals, but he also has a y prime. That's the key. He's a differential equation because he has a y prime. If he had a y double prime, he would be a differential equation. He has derivatives. If he has a y triple prime, same thing. Anyway, in the example, we are given a differential equation. But it says verify. Josh Yang was talking. He was like, I don't want to write the words. I'm like, I know, but this is the whole problem. You have to write down what you're doing or else you won't know how to study it or look back at it. Number 1 says verify this is a... Okay, back in the old days, a solution of a system of equations would be a point that works in an equation in all the equations given, otherwise seen as an intersection on a graph. But that's with systems. Going even beyond, before that, like algebra 1, maybe pre-algebra. If something is a solution, you plug it in and it works. Wait, that's all it's asking? Yeah. You plug it in and it works? So check it, hold on. How can I plug it in? Well, x times minus 3 times. Kiddos, how could I verify this is a solution? What would it look like if I plug this in? What goes in these empty spots? Cx cubed is going to go in the y spot. Does that make sense? Cs cubed goes in the y spot, but then what goes in the other spot? What's the derivative of Cx cubed? Yeah, because 3 is just a coefficient. He chills in front, constant multiple rule, the 3 comes down. Does this work? You guys realize I did this with algebra 1 recently, what the solution is of a linear equation. They had a little xy they plugged in and they were like, true or false. You're the exact same thing, just you need to know how to take a derivative. So true or false? True. Are there tons of these in the AP? No, there are not. But this gives you an idea of what a solution would be. What is a solution to a differential equation? Is it an xy point? No. It's not an xy point. Instead, it's a whole family of Ready? Here's the key. The entire chapter, differential equations. The entire chapter, how do I solve a differential equation? What does the solution look like? Why on earth am I doing a graph of them? Before we can go into any of that, what are the solutions? You guys told me this is a differential equation because it has a what? A y prime. What does the solution have? Just a y. Oh, what's the relationship between a y prime and a y? What is the y in context of the y prime? So therefore, what is the general solution? The general solution is an equation of the antiderivative. But if I'm talking about the general, I'm going to say with. Now, you might wonder why I'm writing it this way. I'm saying with C. Does anybody have a feeling that that should have been different? They're kind of like, why did she write with? I thought she would have written this instead. Or something's missing before the C. Any ideas what's missing before the C? Like, what are you feeling is missing?
Plus.
Right? Because up until now, every single integral formula, every single general antiderivative that we've done, every indefinite integral that we've solved has always had a what? A plus C. But why did I say with C? What do you notice about this guy down here? He doesn't have a plus, but what does he still have?
C.
So how is that possible? I don't get it. Every single one had a plus C, plus C, plus C, plus C. Why would you ever have a times C? We'll figure that out in a second, but first, what's the difference between general and particular? General says, okay, yeah, you can have a constant of integration. You can have a C. Particular, well, hey, check out down below. Isn't particular down here below as well? It says then. We add one more step to this problem. Then find the what? So when it said solution, that was a general solution. We were checking this general solution. It says now keep going to find the particular solution, but how and what do they go on to give us? I'm making it blue on purpose.
Particular solution.
What do they give us? Put it in your handy dandy notebook. We have a clue. Let's use it. They give us something, and with that something, we can plug it in, plug it in. They give us something, and with that something, we can plug it in, plug it in. We don't have to stay clueless. We don't have to stay like, I don't know, it could be anything in the family of all the different possible C's. It's like, no, it can't. For x to be -3 and y to be 2, I'm pretty sure that establishes like an actual solution. We just have to plug and chug to see what it is, right? We would go ahead and plug in the 2 for the y. We would plug in the -3 for the x. We would plug it in context. Ooh, there's a life lesson in there somewhere. Equals, got it, got it, got it, got it. Solve, solve, solve. And what's my C equal for this point to be true? Oh, come on, where are you? Starts with a 2 and ends with a...
Wait, what?
Starts with a 2 and ends with a... I'm just... Find, solve. What is the C?
Constant.
What does it equal? There we go. Did you try to keep saying that and I couldn't hear it? It's just 2 9s. Wow, that was rough. I don't know. It makes sense, right? I was just trying to say, like, what is... It's the constant of integration. Do you guys need to put a name on it? Is that what you were waiting for? We could put a name on it. Remember, he is the guy with plus C, and sometimes it is looking like a plus C, just not always. This is my constant of integration. This is review, but that's okay. I just meant, like, let's solve for C, and C is... Solving for C gives 2 9ths. And then we have my particular solution. So check, I have my verification, dun, 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 and now I have my particular solution. Dun, 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 dun. Check, check, we're done. So particular, what am I going to add? Find C. Let's do this. It's the general solution with, what's particular? The C is particular. With the particular C from, usually, found from, plugging in a given, but they love to also call those givens initial conditions, and initial conditions are exactly like those, hey, start with what you know values from the other day, right? If you know something, you have a starting point. If you have a starting point, you can be specific and get exactly where you want to go, like a particular solution. Okay, so this is me doing one where it's like, hey, verify, check it by plugging in. Plugging in will involve you taking a derivative because it's called a differential equation for a reason. And if you have a clue, make it particular. We haven't talked about how to find it yet. We haven't reviewed, kind of, because you've done a couple of these in the past, just not many, and not like in its own chapter where it was the main guy. But so far, how to verify with some vocab. And so, along those lines, we're going to get to this one that you guys wrote down. We're going to talk about who this graph of these general solutions are. But I want you guys to first go ahead and practice what skill we just did. The skill we just did was verify a general solution. I have up here 1, 2, 3 different possible general solutions. Just to give you a hint, on the AP it might look something like this. That was to make it more like an AP question, so that's a little bit less confusing. They wouldn't use ABC because that would be like your answer choices. They would do something like Roman numeral 1, 2, 3. And your answer choices could be something like 1 only, 2 only, 3 only. Or maybe it'd be something like 1 and 3. Or 2 and 3. Or 1, 2, and 3. They can have all sorts of fun with it. My question is, which ones work in this differential equation? And you'll have to figure that out by plugging in, and plugging in is going to require which derivative for this one. Got to take 2. Ready, set, go. Verify. Which ones work? Meanwhile, are you guys all confused about the 2 9s because it should have been negative 2 27s? Is that what was confusing? Andy just made a solid correction. Solid correction was I should have been plugging in x equals negative 3 when y equals 2 to find the c, and to find the c I would have been plugging it in. I never actually drew an arrow. I should have been plugging it into my general solution, and my general solution would have had not a squared, but a, yeah. And with the cubes, I would have had negative 3 times negative 3 times negative 3, aka negative 27. That would make a bit of a difference. A lot of a difference. Thanks, Andy. Going back one more time, it should have been a cubed when I plugged in that x, and when I plugged in that y, negative 3 raised to the 3rd power, negative 27, so it should have been negative 2 27ths with the x cubed. It's on Jamboard slide number 2 if you guys need it. Right? So as you guys took a couple derivatives, for instance, if I was to look at this guy, y prime would have been cosine, yeah? Y double prime, where are we at? Mm-hmm. For this guy, y prime would have been negative 4 e to the negative 4x, and a lot of people would start asking me the question, why a negative? Who can answer that? U prime. e to the u, derivative of e to the u is e to the u times u prime. So 4e to the u is 4e to the u times u prime, which is negative 1. And so where am I going to be when I come back to the second derivative? Right back to the original. As I just take the derivative of the last guy, c e to the x will just be c e to the x because I just have a constant and an e to the x like a phoenix. Once again, c e to the x. And what do I need to happen in order for this differential equation to be true? I need the second derivative to be the exact same as the original function. Which two are going to have the exact same thing for the second derivative as the original so that when you subtract them, they make 0? Final answer? This guy. Does that make sense? When would number 1 have worked? Third derivative would have been back to a negative cosine. Fourth derivative would have been a positive sign. If this was the fourth derivative minus y. Wait, the fourth derivative, can we go that high? Just super random, off to the side. If we wanted something like the fourth derivative, it starts to get kind of annoying as far as the tick marks. You could start doing things like Roman numerals, but to be honest, what most people do these days, including the AP, they just put a little y to the fourth with parentheses. It doesn't mean raise it to the fourth power. It means the fourth derivative. Just an FYI. Just an FYI. Okay, so coming back. What's the title of 8.1 again? Slope fields. Have we talked about a slope field besides just written stuff down? Writing stuff down? No. So let's check it. In general, the slope field of a differential equation, we've been talking about this dude. It's a dude with maybe dy dx as itself, or maybe it's like a y prime in there somewhere, is defined in the following manner. To every point. Oh. Okay, so we're thinking about points, x's and y's. Assign a small piece of a tangent line. Did you guys write down in the beginning of 8.1 something about small line segments? They weren't talking about any small line segments. They're talking about small tangent line segments. So now all of a sudden we're like, oh, okay, so small tangent lines. That's why I have to be thinking m is coming from my differential equation. Because it's a tangent line. So I'm assigning small little baby tangent lines with a slope of f prime of xy is one snazzy way of saying it. As Andy already said, it's going to be implicitly defined, so we might need to plug in x's and y's to some sort of equation. You can think of it as a dy dx such that xy, or an f prime plugging in xy. It's a mathematical notation there, but the m is coming from the differential equation. And what the slope field is then, remember the main guy of the section, the slope field says once you have attached little baby tangents, little small pieces of tangents to every point in the domain with all the x's and all the y's, then we could say that the slope field will be the collection of all these small pieces of tangent lines with the slope tangent to a curve that passes through the point xy. To be honest, probably as far as like the key idea is everything up here, and then they kind of just restate it in a way in that last sentence. So the slope field says, I take the collection of all of those baby tangent lines. The slope field says, I take the collection of all these baby tangent lines. Let me show you one. You ready? If you want, you could technically switch the order of these. That might be a little bit easier as far as writing them down, but I think I did some stuff over there. So I'm going to leave it for my sake and for the notes to look nice and neat. For your sake, though, you might instead do the graph first. Here's the objective, okay? The objective is to make a slope field for dy dx equals x squared. Super basic. dy dx equals x squared, okay? I'm going to give you some sort of restriction, some sort of size that you're going to be using. We're going to be using from -2 to 2 on the x's, just whatever's shown, and from -2 to 2 on the y's. Okay? And we need to be thinking about tangent lines. Tangent lines that are at points, and then make baby tangents. At points, or where the tangent line goes through. Slope is how sloped they need to be. Now, in theory, we would love to find a pattern. If we can find a pattern, we can do these kind of fast. But making a table, solving for slopes, dy dx is at particular points. I actually have to think of particular points. And so those particular points are something like, maybe I start at something like 0, 0 because I love plugging in 0, 0. Now question, does this differential equation need an x and y? What is this differential equation only in terms of? It only has what variable? Yeah. So I only need to plug in the x. So whether I'm talking about 0, 0, or whether I'm talking about anything else like 0, 1, 0, negative 1, 0, 2, 0, negative 2, no matter what I'm plugging in, what's going to be true about all of their slopes? 0. Because it's only dependent on the x this time. But if it was dependent on the x and y, it might be a little different. But guys, hold on, slopes of 0, aren't they little flat lines? So if I was going to do a little baby tangent line with the approximate slope, just make them all flat, make them all flat, make them all flat, make them all flat, make them all flat. Does that kind of make sense? Because it's in terms of y, anything with x equals 0, anything along that line is going to have little baby flat lines. And you're like, burp, 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 great job. Let's use this and let's go ahead. Okay, we can also then say, what if we were to do anything with an x value of negative 1? And let's just, I don't know, make it in general. Anything with x equals negative 1, isn't the slope going to be a negative 1? Or anything with an x of 1, I'm going to have a slope of positive 1. Or anything with an x of negative 2, I'm going to have a slope of negative 2. Anything with the x of 2, a slope of 2. And remember slope. Slope is rise over run. The 0 was easy, but for these guys, remember you're going to have to do rise over run, over run, over run, over run, over run. We're going back to Algebra 1, everybody. Can anybody tell why I just drew a baby tangent that looks like that? What did I just do? How did I make it? What slope did I need for any of these guys where x equals 1? And isn't a 1 through this point, up 1 over 1, or down 1, left 1? Now, do I want to connect it? No, because that ruins my field. I want a field of all these little baby slopes. It's going to kind of give me trajectories or something to flow through. It gives me something to flow through. But if I have a 1 there, and a 1 there, and a 1 there, look, down 1 over 1, I'm kind of just approximating, but not making it big. I'm making it little. Down 1 over 1, little 1, little 1, little 1. Over here, I'm going to have down 1 over 1, downhill with a 1, downhill with a 1. Right? But what's going to be true as I move to x equals 2?
It's going to be
Steeper. Specifically, I can think now, my graph is, let's go down here. I can go up 2 over 1, or I could think if it helps, I could go back 2, back 1. I just need that 2 over 1 idea. So I always like to just kind of find where I would connect if I was doing a rise over run, and then make it. And once I make one, I just make the rest parallel. This guy over here is going to be down 2 over 1, and then he would connect. You could do rulers theoretically if you wanted to, but no one's ever looking for that type of accuracy.
What do the flat lines represent? Can you see how you did axis on the wheel?
Oh, the flat lines represent little slopes of 0. However, didn't I make a mistake earlier today about plugging in? Right? I did a squared when I was supposed to do a cubed. Question. Have you guys seen me obviously, carefully, actually plug these in? 0 squared was 0. Is there anything else that needs to change, though? Check it. What's a negative 1 squared? So it's not that we're just taking the x, taking the x, taking the x. We were supposed to be taking the x and plugging it in. Nice thing is this one stays the same, so all of those are good. But actually, I was saying these should be negative, but hold on, if we square, it's impossible for those to be negative, right? What should they have been instead? Positive. Okay, well, hold on. If those are positive, they would look the exact same. What's true about these ones, like Benny already said, it's going to be steeper no matter what, but it's actually going to be an up 4 over 1 instead of an up 2 over 1. To be honest, if an AP grader was grading this for you, it would probably just be worth 1 or 2, maybe 3 points, depending on how many graphs you have, how many points you have. But they just need it to be steeper. It would have been positive on the other side as well. And this makes a little more sense if you can think about what the solution to this guy would be. If the derivative is x squared, this one I can solve. This one I could have actually taken the integral of. I didn't need to visualize it because it's one that I can actually use the power rule on. And I would get y is equal to 1/3 x cubed plus c. Once I made my quick little change, because I noticed with the flow that it was incorrect, because I knew an x cubed is what's supposed to be flowing through this field. I looked back, I noticed I hadn't plugged in, I have my plug-in correct, and now I can go ahead and say, what if I want to be flowing through something like, what if they were to give me something like, what if they were to establish a point like 0, 1/2? Yes, we could plug into the equation because we knew how to take the integral and we could solve for that. But what if we didn't know how to take the integral? Then instead we would follow our flow. This is what makes it possible to always visualize the answer to a differential equation if it's impossible to solve by hand. Kiddos, good thing is we have minimum day tomorrow that we're going to keep working on slope fields, but you have the big idea of a differential equation. You can find baby slopes. Well, no, you can find slopes. You make baby tangent lines, and all of a sudden you have this whole field through which solutions flow, whether or not they're possible to be solved. All right, cool kids. I'll see you later. You guys can just attach scans. Let's just attach scans, and I'll extend the deadline till 11:59 to get the scan in. Does that sound good? Okay. Attach scans, and I will go ahead and extend till 11:59. Bye, guys. I was like, yeah.